So today we're going to be talking about kinetics and equilibrium. I'm Aleko.
The Greco. I'm Suhana.
And I'm Nabiha.
First, we gotta define what kinetics actually is.
Kinetics is the description of the rates at which molecules are consumed versus the rates at which molecules are produced.
Kinetics also describes the steps within the chemical reaction.
Here's the collision theory. For a reaction to occur, the particles must collide effectively. What's it called?
An effective collision.
Now, what you need to collide effectively is correct orientation and sufficient amount of energy.
So, what must always occur for a chemical reaction to take place? Effective collisions, formation of a precipitate, formation of a gas, or addition of a catalyst to the reaction.
Pause the video. Pick an answer. We're back with the right answer. Aleka, what was the answer?
Effective collision.
Now, if you didn't choose that...
Clearly, you weren't listening.
So there are various factors that can affect the reaction rate. One of those being concentration, temperature, surface area, the nature of the reactant, and whether or not there's a catalyst present. So an increase in concentration will generally increase the rate of reaction since there's more molecules to work with. An increase in temperature would increase the rate of reaction given the fact that since you need enough energy to collide effectively and actually create a reaction, you're giving the particles more energy. Surface area, an increase in that will increase the potential for a reaction given the fact that it'll just increase the possible collisions. The nature of reactants, someone else can explain that for me.
So the nature of the reactants, the reactions are faster when there are less number of bond arrangements, meaning weaker bonds, faster reaction.
And catalysts. Lower activation energy allowing for a faster rate of reaction. Here's another practice problem.
As the number of molecules per liter of a reactant increases, the number of collisions among reacting particles will...
Pause the video. We're back with the right answer. What was the answer, Greco?
It will increase. Please just call me Aleko.
There's your increase.
Heat of reaction. The heat of reaction is the amount of heat absorbed or released during a reaction.
And here's the equation. Delta H equals heat of the products minus heat of the reactant.
Hey Greco, what does delta mean?
Delta means change, so the heat of the reaction can also be defined as the change in heat.
He's Greek, so he'd know. Endothermic versus exothermic.
A reaction is endothermic if the energy is absorbed during the reaction, meaning delta H is greater than 0, or a positive value. What it means is that the energy of the products is greater than the energy of the reactants.
I'll write that out for you.
And a reaction is exothermic if energy is released during the reaction. Well, which means delta H is less than 0, or it's a negative value. What this means is that the heat of the products is less than the heat of the reactants.
Less.
Here's another practice problem. Okay, if you have a reaction where the heat of the reactants is 15 kilojoules and the heat of the products is 30 kilojoules, what is the heat of reaction?
And we're back to work you through the problem. So, Aleko, can you remind us what the delta H equation was?
It's the heat of products minus the heat of reactants.
So, we see the heat of products is 30. That's not 30. 30 kilojoules. And what are we going to subtract it by?
15 kilojoules.
Now, if you're good at math, your answer is going to be
15 kilojoules.
And there it is. Now, is this reaction endothermic or exothermic?
Well, since the delta H value that we calculated was a positive number, then that means the reaction is endothermic.
Alright, the bottom we got another practice problem. You guys work on this on your own. And we're back to work you through it.
So what is the delta H? If you remember from like 2 seconds ago, delta H equals the heat of the product minus the heat of the reactants.
And the product was 7 kilojoules. So we're going to subtract it by 21 kilojoules. And what's that, Aleko?
That would be negative 14 kilojoules.
The Greeks are good at math. And is this endothermic or exothermic?
Since the delta H value we calculated this time was a negative value, that means the reaction is exothermic.
And there it is. So now it's time to explain potential energy diagrams.
Alright, so here you have the heat of the reactants, where the reaction begins. As you can see, this first diagram is an exothermic process, which is why the heat of the products is lower than the heat of the reactants, because heat was released. Alright, next we see the activation energy, right here. The activation energy is the amount of energy required for the reaction to proceed. From the top of the curve all the way down to the heat of the product represents the activated complex, the point of maximum energy in the reaction path. And then we have the heat of the products, way down here. Now, as you can see, we have some dotted lines here representing the reactants and the products, and the difference between those lines is the heat of reaction, which we just explained.
Now let's try to work on a practice problem.
Wait, wasn't that? No.
So let's practice naming the lines Nabiha just explained. Pause the video and label these on your own. Okay, so we're back. Aleko, what letter is the heat of reactants?
So the heat of the reactants would be line A. The heat of the products would be line E.
Alright, you're getting a little ahead here. Didn't ask. But what's the heat of reaction, Nabiha?
The heat of reaction is line D.
Oh. Where's the activated complex, Nabiha?
Line C.
Leko's out here pouting. You know what? Tell us what the activation energy is.
The activation energy is line B. I wasn't pouting.
And there you go. Just for fun, can one of you tell me if this is an endothermic or exothermic process?
Well, it's an exothermic process.
And how do you know that?
Because the heat of the products is lower than the heat of the reactants.
Nabiha, what's another way you could tell?
Well, you have heat on the product side of the equation. That means it was released.
And that's another way to know it's exothermic. Equilibrium!
Okay, equilibrium. In a reversible reaction, equilibrium is established when the rate of the forward and backward reactions are equal. Remember that word, rate.
Rate!
Rate.
Are equal. Leko, just to bring home the point, can you read the second one?
So the rates of the forward and reverse reaction must be equal, but the concentrations do not.
The concentrations don't matter.
Yep. They do matter in a sense, given the fact that concentrations do have to be constant at equilibrium. They don't have to be equal, but they have to be the same.
So they kind of do matter. That's fine. Now there are different types of equilibrium.
Really?
In physical equilibrium, we have phase equilibrium, also known as dynamic equilibrium.
Think of these as physical changes. For example, when water boils, you've got the liquid phase and the gas phase at the same time.
Whoa! Because it matters.
Since you should know your heating and cooling curves by now, we'll just show you one. What do you want me to draw, Leko?
How about a heating curve?
Okay. Should look something like this. You guys recognize that? Now, Nabiha, where would liquid and gas be at equilibrium?
Well, right here.
Guys, remember that? You should. And then solid and liquid would be at equilibrium over here.
Yep.
That's why it goes a little flat over here, if you didn't already know.
Now, Leko, why is this called equilibrium again?
It's called equilibrium because the rates of the two reactions are equal.
And the concentrations, right?
No, that means the concentrations are constant at equilibrium.
Oh, you're right. Now, other types of equilibrium.
Solution equilibrium. For example, solids reacting in liquids, gases reacting in liquids.
And then there's chemical equilibrium.
That would be reactants producing a new substance, which would be carbon monoxide and oxygen forming carbon dioxide.
Now, who's going to try to say this name?
So this would be, Le Chatelier's principle, which is when stress is added to a system, the equilibrium will shift in whichever direction will relieve the stress.
We know all about stress, right?
I know too much.
Now, there are 3 kinds of stress that will affect a system: concentration, temperature, and pressure.
Wow.
And some of us use acronyms to remember these. Now, I'm going to explain them in the coming up slides, but here they are. Good. Use these on test to help you. Now, here it is. Change in concentration.
You have CIA. Concentration increases
away. So what that's saying is when the concentration of a substance on one side increases, the equilibrium will shift towards the opposite side.
Now, for example, if more of B is added, where will the reaction shift to relieve the stress?
It's right there on the slide. It will shift to the right.
Why, Leko?
Well, because there's a higher concentration of the. Can we pause that? So it will shift to the right because it needs to relieve the stress on the system.
And what's going to happen to the concentrations of C and D, Nabiha?
They're going to increase because they're in the direction that the reaction's going to move.
And then concentration of A?
That's going to decrease since it's on the side where the equilibrium is shifting away from.
Now here's a practice problem. Let's pause the video and you can work on it on your own. Alright, that was enough time. We're back and we'll help you through it. So, if the concentration of C is increased, which way is it going to shift, Nabiha?
It's going to shift left. Huh, bet you thought it was going to go forward. It's not.
Nope, it's going to go left. And what's going to happen to the concentrations of A and B, Aleko?
Well, since the equilibrium is shifting to the left, then that means the concentrations of A and B will increase.
And the concentration of D, Nabiha?
That's going to decrease.
Wow.
And why is that?
Because the reaction is shifting to the opposite direction of D.
So more of D will be consumed. Now our next acronym is TIA.
When there's a temperature increase, equilibrium shifts away from the side where it's increased. So, like it said, when heat is added to one side of the reaction, equilibrium will shift in the opposite direction. When temperature is increased, the reaction will shift in the endothermic direction so that heat is absorbed. When the temperature is decreased, the reaction will shift in the exothermic direction so that heat is released.
So one more time, Nabiha. When temperature is increased, it shifts away from
the side where the heat was added.
Now here's an example. If the temperature is increased, which means this energy will increase, the reaction will shift
To the left.
and then concentrations of A and B will
Increase,
and C and D will.
decrease.
Now here's a practice problem for you guys at the bottom. Alright, I hope you figured it out by now. If heat is added, this energy will increase. What happens, Aleko?
The equilibrium will shift towards the right.
And what happens to the concentration of C and D, Nabiha?
They're going to increase.
Yay! Now our next acronym, PIL. Pressure increase, less. Explain it, Aleko.
So, the thing that's different about this type of stress is the fact that a change in pressure can only affect the reaction if there are gases present. So if there's no gases in your reaction, then any change in pressure won't cause the reaction to change at all. So, when the pressure of a system increases, equilibrium will shift to the side that has a smaller number of molecules, and vice versa. If pressure decreases, equilibrium will shift to the side with more molecules.
Now here's an example. Let's assume all of these compounds and elements are gases. So when the pressure increases, the reaction will shift right. Why, Aleko?
Because there's less moles of gases on the right side.
Let's add them up, Navia. How many moles are on the left side?
Well, you got 1 mole of nitrogen and 3 moles of hydrogen. So you have 4 moles of gas.
And how many you got over here?
2.
What's going to happen to the concentration of ammonia?
It's gonna increase.
And the concentrations of nitrogen and hydrogen?
Decrease.
Now here's an example. Pause the video and work on it. Alright, that was enough time. We're back. Okay. Now Nabiha, walk us through this problem.
So, assuming, again, that these are all gases, which they are, if the pressure of the system increases, the equilibrium will shift. Let go.
It's gonna shift to the left.
Sure. And the concentration of N2 will
Decrease.
decrease. Okay, if the temperature, which is on the left side, which means it's
Endothermic!
right. So if the temperature is decreased, the reaction will shift, let go,
To the left.
to the left. And the concentration of NH3 will
Increase.
increase.
Amazing.
Amazing. Alright. Now, if the concentration of H3 increases, Which way is the equilibrium gonna shift, Aleko?
It's going to shift to the left.
Like that
To the left.
Beyonce song.
I
Okay,
need
just
it.
continue.
Irrelevant. Okay. What about what's gonna happen to the concentration of N2?
It's going to decrease.
It's gonna decrease. You're right.
Thank you.
Nobody wants N2. Alright. What if I take away some of that NH3, Suhana? What's gonna happen to the reaction?
To the left, to the left, to the left, to the left.
It's not even the song. That's not the
Cupid
Beyonce.
Shuffle.
It's not the Beyonce song.
I wanted to mix
You're
it
gonna
up a
confuse
little.
the kids.
Alright,
Okay.
it's fine.
Okay, so
Concentration of N2 will
take it away, Aleko.
Decrease.
Decrease. Good job, Aleko.
Thank you.
Now, let's talk about the strategies we used to figure out each problem. Aleko, what did we use for the first one?
We use the PIL acronym.
And then what about the second one, Nabiha?
We use the TIA.
Third one, Aleko?
CIA.
No, we're not talking about the government agency, am I right?
Ha!
Okay, next one.
Oh, CIA again.
Oh my god, they're watching.
Wow, you're so funny.
Anyways, catalyst.
So, a catalyst is simply a substance that increases the rate of reaction without actually participating within the reaction. This is because when a catalyst is added to the reaction, it lowers the activation energy.
But does it affect the heat of reaction?
No, the heat of the reaction remains the same.
So catalysts don't affect the heat of reaction. So let me draw a curve for you. So there's a potential energy diagram without a catalyst. Now, Aleko, how would it look with the catalyst?
Well, it would start from the same line. It would go to the same lines as the heat of products and reactants,
Mm-hmm.
only it would be slightly lower in the middle, meaning that the activation energy was lowered. So a catalyst does not affect the heat of products or the heat of the reactants at all.
So they start at the same place,
Exactly.
and then they end at the same place.
Yep. The only thing that changes is the heat of the reaction.
Alright, I think we're good here.
Yeah, hope you guys learned some chemistry.
Yep.
Good luck. Should I say a pun for them?
No.
You know what? I'll save you guys this time. You don't need my puns.
Yeah, because they're bad.
Okay, good luck, guys.